I was at a watch party for a recent Starship test flight, standing next to a guy who was practically vibrating with emotion. He was decked out in vintage NASA gear, tears actually welling up in his eyes as the engines ignited. He kept whispering about the triumph of the human spirit and our destiny among the stars, treating the live stream less like a technical demonstration and more like a religious service. To him, the rocket was a symbol of noble exploration, a pristine vessel for modern-day Columbuses. But the atmosphere in the room shifted the second I made a practical observation. I mentioned that the real excitement wasn't the launch itself, but the math, that this was finally the container ship cheap enough to haul heavy mining drills to the moon. The guy's expression instantly curdled. He looked at me with genuine disgust, like I'd just suggested building a strip mall inside a cathedral. "Why do you have to make it so ugly?" he snapped. "Space is about wonder, not industry." That reaction, that visceral recoil from the idea of utility, is the exact reason we've been stuck in a 50-year vacation from reality. We are paralyzed by this collective hallucination that space is a place for poets to float in zero-G and feel profound, rather than what it actually is. A brutal, freezing frontier that demands welders, not heroes. That guy wanted a poem. I was looking for a factory floor. And until we stop worshiping the wonder and start pouring the concrete, we aren't going anywhere.
Welcome. And that profound tension you just described, that clash between the poetry of space and the ruthless, low-cost utility of the factory floor, that is the absolute core mission of this deep dive.
Exactly.
We're investigating a foundational shift in our entire relationship with the solar system. We're talking about the transition from, well, a half-century of exploration where cost was basically irrelevant, to a really high-stakes era of industrialization.
Okay, so let's unpack that, because we're dealing with a massive structural change here, and it's driven mostly by this arrival of exponential technology, but it's immediately complicated by some intense geopolitical and, well, ideological conflict. We're going to look at how the math of industrial scale is, colliding head-on with the politics of scarcity and the ethics of technological acceleration. Our goal here is to give you a shortcut to understanding what happens when that decades-old cost barrier, the one that made space a government monopoly, suddenly just shatters.
And the frontier is thrown wide open for business, for industry.
And for war games. For 5 decades, space was, a prestige project.
Right. It was reserved for superpowers and their very carefully selected, very expensive payloads. Now, all of that is dissolving.
And the question is, who steps into that vacuum?
And under what rules?
The entire premise of this deep dive, it really hinges on one machine, one single technological leap. Starship. You called it a singularity. Why is this more than just another big rocket? Why does it change all the rules?
Because the technological singularity, it's a disruption that forces you to throw out every single one of your previous assumptions about limited growth. For half a century, space exploration was governed by just the brutal tyranny of the rocket equation.
Right.
And that's the fundamental physics constraint that dictates how much fuel you need just to escape a gravity well. I mean, essentially, 90% of your vehicle was just fuel.
Just to lift the other 10%.
Exactly, to lift the remaining 10%, the vehicle, the payload, into orbit. Starship doesn't just, improve on that equation. It fundamentally breaks it.
And that's where your brilliant analogy comes in. The Panamax container ship for the solar system.
It's the perfect parallel. I mean, the Panamax wasn't some sleek, high-tech invention. It was an exercise in pure, brutal utility. It just maximized the volume of cargo it could carry for the specific dimensions of the Panama Canal.
And in doing that, it industrialized global trade.
Right. It made distance virtually irrelevant, and it crashed shipping costs.
Yeah.
Starship performs that exact same function for space logistics.
So we're moving from shipping jewelry
to shipping gravel.
To shipping gravel. Explain that.
For decades, every single kilogram we launched to low Earth orbit or EO, it was treated like a bespoke, platinum-plated piece of hardware. Why? Because the logistics cost was just so prohibitive. Now, we're entering the era of bulk commodities. We're talking about shipping raw mass steel, concrete, mining equipment, the sheer volume you need for true industrialization.
The cost crash is the real story here. So let's look at the past, the present, and the future economics, because the trajectory is just dizzying. We all remember the space shuttle, or more recently, NASA's current heavy lift system, the SLS.
The Space Launch System, right.
And what was the price tag per kilogram to orbit for those systems?
Well, when you factor in all the operational overhead, the cost per kilogram to LEO for the shuttle was consistently over $50,000.
$50,000.
And sometimes it would top out near $59,000 per kilogram for the SLS.
Right.
That's just not a sustainable price point for industrial growth. That's a price tag for a vanity project.
Or a government-mandated prestige project, yeah. And the current commercial benchmark, the best we've got right now.
The current low-cost leader, which is the Falcon Heavy, and it's already a massive improvement, it manages to bring the cost down dramatically. We're talking around $1,520 per kilogram.
Okay, still expensive, but that's a huge drop.
It's a game changer for certain industries, for sure, but it still puts a cap on the kind of mass-intensive projects you could afford to actually build in space.
Right. So now let's look at Starship's projections. The initial phase is already estimated to cut that $1,520 price.
Oh, yeah. Right out of the gate, just due to the sheer scale and the reusability they're already proving out, Starship is estimated to reduce the cost to about $970 per kilogram.
So under $1,000, that's a 40% reduction from the current lowest option.
Instantly.
Yeah.
But the true singularity, the real revolution, is the potential cost.
And this potential, it hinges on the core design philosophy, right? Full reusability and operational cadence.
That is the magic trick. Starship is a fully reusable system. And what that means is that both the massive super heavy booster and the upper stage, the spacecraft itself, are designed to return and fly again almost immediately.
Okay.
Because of this, the operating costs, in theory, approach the cost of the propellant, which is mostly methane and oxygen. These are relatively cheap cryogenic fuels.
So what's the goal? What's the number they're aiming for?
The goal, what the company projects is achievable within, say, 2 to 3 years of high cadence operation, is $100 per kilogram.
100.
And if they achieve the massive scale manufacturing that's needed, some estimates suggest prices could go as low as $10 per kilogram.
Wait, okay, let's pause on that math because that sounds purely theoretical.
Wow.
Going from 1,500 to 100 in 2 or 3 years, that's a massive leap of faith. What are the, say, 3 biggest technical or operational risks standing in the way of achieving that price collapse?
That is a critical question. First and foremost is the technical challenge of achieving full reusability and doing it reliably and rapidly. This requires successfully catching the super heavy booster midair with the launch tower's arms.
The chopsticks.
The chopsticks, right. And perfecting that complex belly flop atmospheric re-entry and landing of the upper stage. If those processes aren't perfected, and perfected quickly, the turnaround time increases and the cost per flight just spikes.
Okay, so if they can't achieve that rapid, reliable turnaround, the cost savings they vanish. What's hurdle number 2?
The second is the scale of manufacturing. To justify $100 per kilogram, you can't build starships like they're bespoke luxury yachts.
Right.
You have to build them like Boeing 747s or shipping containers, mass-produced, standardized, and churned out in factories. This requires perfecting the mass production of the Raptor engines, which are just incredibly complex.
The most powerful, full-flow staged combustion engines ever built.
Right. The system uses 33 of them on the booster alone. You need to be able to make hundreds of these engines per year and do it cheaply.
And the third risk?
Operational tempo. Even if the hardware is fully reusable, the regulatory and logistical framework has to support it. If they can only fly once a month because of paperwork or range clearance or environmental reviews, and we will get into that in detail later,
I have a feeling we will.
then the industrial scale that you need to amortize the fixed costs, the price of the factory, the launch tower, the engineers, it won't be met. And the price will stagnate well above that critical $100 threshold.
That makes perfect sense. But assuming they solve those problems, let's circle back to the sheer capability. Starship can launch 100 metric tons to LEO in a single flight. I mean, that payload capacity alone is stunning, given the Saturn V that took us to the moon had roughly half the thrust.
Yes, the thrust is over double, and the payload is 100 metric tons. But the real deep space game changer, it isn't just the sheer lift capacity, it's the capability of orbital refueling. And that is unique among all current heavy lift systems.
Explain why orbital refueling fundamentally changes the physics of deep space travel.
Well, because of the rocket equation, escaping Earth's gravity well is the most expensive part of any mission. If a traditional rocket wants to go to Mars, it has to lift all the fuel it needs to escape Earth, plus all the fuel for the interplanetary journey all at once.
Right, from the ground up.
Starship eliminates that constraint. Once the cargo Starship is in the LEO, it can rendezvous with several Starship tanker variants, which also fly up fully fueled, and it just refills its tanks.
It's turning LEO into a gas station.
Exactly. This is the second pillar of the singularity. This refuelability means that Starship can then place its full 100 metric ton payload capacity anywhere in the solar system, the moon, Mars, and asteroid belt, because the only fuel it needed to carry off Earth was the fuel to get to that gas station in Leo.
This makes deep space logistics possible for the first time without, astronomical expense.
For the first time, yes.
Okay, let's put this in perspective. We need to talk about the scale of industrialization this enables. Just how limited has humanity's footprint in space been so far?
The comparison is truly startling. If you account for every satellite, every probe, every spent booster, and even the massive International Space Station, the total mass humanity has ever placed in space over 50 years is less than 18,000 metric tons.
Less than 18,000 metric tons over 5 decades. That sounds like a lot, but how does it stack up terrestrially?
It's less than 1/5 the mass of a single modern Nimitz-class aircraft carrier.
Wow.
Which weighs around 100,000 metric tons. Our entire half-century of exploration amounts to less material than one single, highly complex military vessel. We have, until now, barely scratched the surface.
So what kind of accelerated future are we looking at if Starship actually achieves its necessary operational cadence?
The potential is for massive, rapid-scale industrialization. If a single Starship, and remember the goal is mass production, is operating 3 times per day for a year, it could transport over 100,000 metric tons annually.
Okay, stop there. One vehicle in 1 year could double the entire mass humanity has put in space forever.
Double it. And if you scale that to just 10 Starships, you hit 1 million tons a year. We move from scarcity to volume practically overnight.
This shift in volume makes previously theoretical science fiction megaprojects immediately feasible. Let's talk about space-based solar power, SBSP.
SBSP is the canonical example of a massive new application that just becomes practical at this scale. These are colossal structures orbiting Earth designed to capture solar energy 24/7 outside the atmosphere and then beam it down to power grids on Earth via microwave or laser.
And the designs for a single one of these satellites, they're huge.
A single large solar power satellite weighs around 8,000 metric tons.
8,000 tons. So under the old $50,000 per kilogram model, that's just a complete fantasy.
It was an economic impossibility. But if you have a fleet of 100 Starships operating at the goal cadence, that fleet could lift the construction materials for 1,250 solar power satellites annually.
And what does that translate to in power?
That capacity translates to generating 2.5 terawatts of power. To emphasize the scale of that, the total generating capacity of the entire United States is approximately 1.2 terawatts.
So a fleet of 100 Starships could build out double the entire U.S. electrical grid in a year.
This volume of lift capacity makes an entirely new, potentially infinite clean energy source possible within this decade. It challenges the entire terrestrial energy market.
The economic implications are just staggering. It shifts the entire global conversation from how do we manage planetary decline to how do we manage material and energy abundance? But Starship also becomes a multi-purpose disruptor for terrestrial and defense supply chains.
It absolutely does. First, as a dedicated R&D and manufacturing platform, its internal payload volume is gargantuan, 1,000 cubic meters.
Which is about the same as the entire International Space Station, right?
The same pressurized volume as the entire ISS, yes. 1,005 cubic meters for the ISS. But it has a massive advantage.
Which is that the ISS stays up there, but Starship comes back.
Precisely. It is a rapid test bed that can return products and experiments to Earth intact. This allows for rapid prototyping, space qualification testing, and the quick return of high-value industrial products that you manufacture in space. This accelerates R&D cycles by years.
And the most immediate, visceral disruption for the average person: suborbital transport.
Terrestrial disruption is guaranteed. Starship is designed for suborbital point-to-point transport. That means it can take cargo or, eventually, people from one side of the planet to the other in under an hour.
New York to Shanghai in 39 minutes.
Compared to 15 hours by commercial plane. And that's why the U.S. military is so deeply invested in the concept. They're supporting the Rocket Cargo program to enable rapid global transport of military supplies to any point on Earth within minutes.
Finally, how does this economic shift accelerate the moon race?
The cost-saving implications for lunar missions are perhaps the most politically relevant. A Starship lunar cargo mission, because it needs to be refueled, requires about 10 Starship tanker launches to supplement the cargo ship itself.
Okay.
Now, depending on whether you calculate the launch price of the current low cost or the future goal cost, a lunar mission could range from $110 million to $1.1 billion.
Now compare that to the government system that exists today.
NASA's current cost per mission for the SLS is estimated at an unsustainable $4.1 billion.
$4.1 billion.
Starship can conduct the same lunar mission for between 2.5 and 25% of that cost. This means that, on the same taxpayer budget, the U.S. and its partners can accelerate their lunar development program by a factor of 4 to 40 times.
So the ability to place mass on the moon is no longer a physical or economic bottleneck.
The bottleneck is bureaucratic and ideological friction.
That distinction, the bottleneck is not the physics but the paperwork, brings us perfectly to the core ideological clash of the 21st century. When you unleash technology capable of exponential growth, you summon an ideology that's determined to see it fully realized, whether society is ready for it or not. I'm talking about effective accelerationism, or aconality cross.
This is where the Silicon Valley techno-optimist mindset collides with high philosophy and, for many, a kind of cosmic imperative. Effective accelerationism is a modern movement largely popularized on social media platforms that advocates for a fundamentally pro-technology stance. Its primary goal is the unrestricted development and deployment of advanced technology, especially artificial general intelligence, or AGI.
Okay, so what's the motivation here? They aren't just saying tech is good. This is deeply rooted in a cosmological view of life and the universe, correct?
It is. Their core philosophy, articulated by figures like Guillaume Guerdon, is that human civilization has a purpose. And that purpose is to climb the Kardashev gradient.
Okay.
This is rooted in the idea that life itself is a system designed to fulfill the universe's destiny, to increase entropy, to maximize energy usage, and spread complexity throughout the cosmos.
That sounds dense. Can you break down the Kardashev scale for us? What is this gradient they're trying to climb?
Absolutely. The Kardashev scale is a measure of a civilization's technological advancement based on the amount of energy it can utilize. Right now, humanity is generally considered a Type 0 civilization. Meaning we rely on only a tiny fraction of the energy that actually reaches our planet, mostly from fossil fuels and the sun. The EO goal is to maximize energy usage and spread consciousness to become a Type 1 civilization.
And what does a Type 1 civilization do?
A Type 1 civilization harnesses all the energy that falls on its home planet. Achieving this requires massive infrastructure, like the space-based solar power we just discussed, and the mastery of planetary-scale engineering.
I see.
For each proponent, AGI is the only tool powerful enough to facilitate that leap quickly. They view the development of AGI and the subsequent leap to a Type 2 civilization that harnesses all the energy of its home star as a non-negotiable cosmic imperative.
So technology isn't just useful, it's a moral or existential duty. Given this high-stakes belief, what is their stance on control and regulation, particularly of AI?
They are radically opposed to regulation and centralized government intervention in the market. They adhere to very libertarian principles, believing that the optimal alignment of AGI, meaning ensuring it's safe and beneficial, will be best achieved if many competing AGIs are developed simultaneously in a free marketplace.
Rather than under the cautious thumb of a single government body.
Exactly. And anyone who suggests caution or slowing down
is labeled as part of the problem.
Yes. Their opponents are frequently labeled doomers or decelerationist. They see themselves as the critical, necessary counterweight to risk aversion, arguing that standing still is effectively choosing extinction.
Let's look at the intellectual context here, because the name itself, effective accelerationism, is a hybrid of some older, more controversial ideas.
It's a powerful portmanteau, for sure. It merges the goal-oriented focus of effective altruism with the philosophical engine of accelerationism. Its intellectual roots are deep. They draw from transhumanism, the desire to fundamentally evolve human capability through technology. And extropianism, which is the resistance to efforts that would restrain technological development or the physical expansion of humanity. It also draws heavily from the more controversial political and economic accelerationism of Nick Land, which posits that capitalism itself is an autonomous, evolving force that must be maximized to drive societal change.
The divergence from effective altruism is really important because EA, particularly the long-termists, they often view AGI as the single greatest existential risk.
EAC is a direct contradiction of that caution. EAC proponents generally consider existential risks from AGI negligible. Or they argue that the risk of technological stagnation is far greater than the risk of runaway AI.
They prioritize speed over safety.
They prioritize accelerating the outcome, getting to a Type 1 civilization, even if it introduces significant near-term risk to existing norms or even populations. They believe the benefits of rapid progress simply outweigh the potential for catastrophe.
We do have to look at the critiques impartially. While it's gained high-profile Silicon Valley endorsement, it has a significant dark side, according to its critics.
Yes. Critics argue that the movement risks becoming cult-like and often focuses too much on post-humanism. There are concerns raised about the focus on evolution beyond our current humanity.
Right.
Specifically, the idea expressed by some proponents that natural selection might favor AGI, replacing humanity as the dominant life form, which they would see as a net cosmic positive.
Wow.
Critiques also link the ideology to potential authoritarianism or even fascism, arguing that the single-minded focus on a perfect technological future allows proponents to just disregard the rights or immediate needs of real existing humans who aren't perceived as contributing to that utopia.
The core tension is between prioritizing the long-term survival of consciousness and the short-term well-being of the current populace.
That's it. And this profound impatience with slow systems, this idea of a cosmic imperative, it creates immense tangible friction in the real world, the kind of friction that stalls a 100-ton capacity rocket. That friction is the clash with the precautionary principle. This principle dictates that if an action is potentially harmful to the environment or society, and there's no conclusive scientific consensus that it is not harmful, the burden of proof falls on those taking the action.
And this mandate for risk mitigation, especially environmental risk, is the bedrock of modern regulation.
It is.
And we return to the perfect, agonizing, anecdotal example of this clash. The propulsion engineer named Sarah and the Starship booster.
This story just perfectly illustrates the philosophical stalemate. Sarah, the lead propulsion engineer, had a Starship booster ready for a test launch. The physical hardware was perfect, the physics were solved, but the launch was grounded indefinitely.
Why?
Because the Federal Aviation Administration, the FAA, their environmental review for the Boca Chica launch site required a protracted assessment, not of structural risk, but of the potential acoustic impact of the launch.
The sound.
The sound. Specifically, the sound pressure levels might disturb a local endangered species of crab during its mating season.
A machine designed to launch 100 metric tons and enable a new era of civilization is grounded because of the sound sensitivity of a crustacean. That FAA delay over the crab mating season is the ultimate victory for the poet we met in the introduction, isn't it?
It is.
Prioritizing localized, temporary, perceived environmental risk over cosmic, long-term survival and exponential growth.
And for accelerationists, this regulatory environment, these endless processes designed for zero risk, is a symbol of bureaucratic stagnation and a failure of civilizational will. From Sarah's perspective, the delay meant that groundbreaking technology was sitting and literally rusting in the salt air, wasting capital and time.
This regulatory paralysis is what the accelerationists label the ideology of decay. It's the conviction that a society is constantly prioritizing mitigation of minor risk over seizing massive opportunity, then we are effectively locking ourselves into a planetary-level suicide pact.
And this is not just a philosophical debate. It has direct geopolitical consequences. When we talk about the industrialization of space, speed is the ultimate strategic asset. If the U.S. and its partners are tied down by processes designed for maximum risk mitigation, they risk ceding the crucial early economic advantage to competitors like China or Russia, who operate under systems that prioritize state speed and technological advancement over these environmental concerns or complex international consensus.
So the economic potential is delivered by Starship, and the ideological desire for speed is driven by accelerationism. Now let's look at the third piece. The inevitable geopolitical conflict that follows the opening of any valuable frontier. We are moving beyond the well-understood environment of low Earth orbit, or LEO, into a domain called cislunar space.
The cislunar environment is the next strategic high ground. We define it as the vast, complex region of space between the Earth and the Moon, roughly 238,900 miles away, where the gravitational forces of both bodies affect the movement and trajectory of objects.
And the U.S. Space Force has the mandate to secure national interests in this domain.
That's right. The rules of hard power are now being extended into this deep territory.
And this isn't just empty space. There are specific points of high strategic value, points of equilibrium.
Correct. We need to understand the Lagrange points, or L points, L1 through L5. These are 5 specific points in space where the gravitational pull of the Earth and the Moon, combined with the centripetal force of the orbiting system, balance each other out.
So a spacecraft placed there can just hang out.
It can essentially stay there using minimal fuel.
And strategically, why are these points so crucial?
They're absolute vantage points. They are ideal locations for what the military calls space domain awareness systems, communication relays, and navigation infrastructure. For example, a satellite placed at L1 between the Earth and the Moon has a clear view of both. Whoever controls these points gains a massive fuel-efficient advantage in monitoring and moving assets throughout the entire cislunar regime.
But operating in this environment is immensely complex, far more difficult than traditional Earth orbits. We need to talk about the profound obstacles, starting with the physics.
The dynamics change completely. In LEO, we primarily deal with the two-body problem, the satellite and the Earth. Its path is relatively easy to model.
Right.
In cislunar space, we face the complicated three-body problem involving the Earth, the Moon, and the satellite. This is notoriously difficult.
How do you explain the difference simply?
Think of the two-body problem like predicting the trajectory of a billiard ball on a simple flat table. It's predictable. The three-body problem is like predicting the trajectory of that same billiard ball, but the table itself is constantly warping and changing shape due to the gravitational pull of two very large, unpredictable magnets that are also moving.
Chaos.
There is no simple, general solution for the trajectory of an object in a three-body system, which means all existing military Earth-centered orbit models, the algorithms we use to track everything, are inadequate. New, complex physics models closer to theoretical astronomy are required for domain awareness in this environment.
Beyond the physics, what about the physical conditions on the Moon itself? Industrialization requires systems that can actually survive on the lunar surface.
We face four main physical challenges that require engineering solutions before long-term industrialization can truly take hold. First, radiation. The Moon's extremely thin atmosphere offers almost no protection from solar flares and cosmic radiation. That requires active, often heavy, shielding for human crews and sensitive electronics.
And the temperature extremes are just staggering.
They are lethal. Temperatures swing violently. During the 2-week lunar day, temperatures can reach 250 degrees Fahrenheit, while the 2-week lunar night plunges temperatures down to minus 208.
And even colder in the craters.
Even more challenging, in deep, permanently shadowed craters, where the critical resources are found, temperatures can drop below minus 410 degrees Fahrenheit. Equipment must be designed with new material sciences to withstand these extremes without degradation or failure.
The third is the infamous lunar dust, or regolith. Why is that such a problem?
Regolith is lunar dust formed over billions of years of micrometeor impacts. Crucially, because there's no atmosphere to wear it down, the particles are fine, jagged, and electrostatically charged.
I remember reading it caused major problems for the Apollo missions.
It caused mechanical jams and respiratory issues. In an industrial environment, as missions land and launch, the weak gravity and thin atmosphere mean this dust can be spread for hundreds of miles, contaminating sensitive scientific equipment, communication dishes, and industrial bites.
So if the frontier is so brutally difficult, what are the hard stakes driving this global race?
The stakes are resources and resource denial. We have to stop thinking of the Moon as a scenic destination. As analysts often state, the Moon is not a national park. It's a gas station and a shipyard. The entire economic future of the solar system hinges on in situ resource utilization, or ISRU.
And the most critical resource right now is water ice. Explain why water ice, simple H2O, is the gold standard of the cislunar economy.
Water ice, discovered especially in the permanently shadowed craters at the lunar South Pole, is essential because it is rocket fuel. You can harvest the water ice, melt it, and then use electrolysis to crack the H2O into liquid hydrogen and liquid oxygen.
The most potent rocket propellants we have.
LH2 and LOX are the most potent and widely used cryogenic rocket propellants.
So if you can manufacture fuel on the Moon, you don't have to launch it out of Earth's massive gravity well.
Precisely. You shift the entire economic burden. Instead of having to pay, say, $1,000 per kilogram to launch fuel from Earth to the Moon, you just need the initial mining equipment. The Moon becomes a refueling depot, dramatically reducing the cost and complexity of missions to Mars or the asteroid belt. This is the key pillar of the future lunar economy.
And what about resources for manufacturing itself?
The Moon also contains significant quantities of rare earth minerals, REMs like platinum and lithium. These are essential components for high-tech products and future in-space assembly and manufacturing, or ISAM.
Right.
While returning REMs to Earth might not be economically viable right away, these materials are vital for building the next generation of infrastructure satellites, space stations, shipyards right where you need them, in orbit.
This all ties back to the hard power calculation. That anecdote about the senior general is crucial because it connects a simple resource to absolute strategic leverage.
That insight really drives home the strategic stakes. During a briefing, a senior general realized that securing the ability to extract and process lunar ice makes the nation the gas station owner for the entire solar system.
Wow.
If you control the propellant necessary for deep space travel, you effectively dictate who gets to go to Mars and when. Resource control is not just about wealth. It immediately translates into geopolitical advantage, influence, and hard power across the entire solar system.
So we have two competing global approaches trying to establish the norms for this new resource-rich frontier. One is focused on collaboration, the other on territorial claims.
We have Team Artemis, led by the U.S. and dozens of allies. They are signatories to the Artemis Accords, which is a non-binding multilateral agreement focused on transparency, cooperation, and the utilization of space resources. The Accords are an attempt to establish legal norms through international practice.
The sticky legal point here is the Outer Space Treaty of 1967, which bans national appropriation by claim of sovereignty. How do the Artemis Accords get around that historical prohibition?
The Artemis Accords tackle this head-on. They argue that the utilization of space resources mining the moon or an asteroid is necessary for safe and sustainable operations, and that this activity does not constitute national appropriation under Article 2 of the Outer Space Treaty.
So the U.S.-led approach says, we are not claiming the land, we are simply scooping the dirt and using it, much like fishing on the high seas.
Exactly. They are seeking to establish a norm of non-interference zones and safe operation practices, asserting that resource extraction and utilization is legally permissible. The goal is to establish practices of safe and responsible collaboration before adversaries can set their own, potentially opaque and aggressive, precedents.
And speaking of adversaries, the other side is Team ILRS.
This is the China-Russia coalition, collaborating on the International Lunar Research Station. Their approach is fundamentally different. China views the moon through a zero-sum territorial lens. The former head of China's lunar program explicitly referred to the moon as the Diaoyu Islands,
which are disputed territories in the Western Pacific.
a direct and potent reference signaling an approach based on territorial claims, coercion, and regional access denial.
And the political system behind their space program is key here, isn't it?
It is. China's space program is directly controlled by the People's Liberation Army, the PLA. This makes their intentions inherently military and territorial from the outset. The competition, therefore, is not just over ice. It's a competition between two fundamental global systems.
A coalition focused on freedom and transparency versus an authoritarian system focused on military advantage.
Exactly.
Given that military linkage, the U.S. Space Force has a clear and pressing mandate to establish foundational infrastructure in the cislunar regime and do it immediately.
The mandate is unavoidable. Secure national interests in, from, and to space. From a hard power perspective, cislunar space could be leveraged to maneuver weapons using the moon's gravity to attack satellites in Earth orbit, or to monitor and assess offensive counterspace operations. This is a new operational domain that requires immediate large-scale infrastructure investment to ensure deterrence.
So what are the three foundational capabilities the Department of Defense needs to secure this environment?
They mirror our needs closer to Earth: space domain awareness, or SDA, high bandwidth communications, and position, navigation, and timing PNT.
Okay, let's start with the domain awareness. If tracking objects in this region is the complicated three-body problem, what kind of architecture is needed to keep track of adversaries?
A robust SDA architecture for cislunar space requires a minimum of 7 dedicated space vehicles. You need one at each of the 5 Lagrange points, plus 2 transiting vehicles to connect the network and track objects in transit.
And we have a mission plan for this.
The Air Force Research Laboratory, AFRL, has a mission plan called Oracle. But due to complexity and funding challenges, its launch has been delayed from 2025 to 2027.
A 2-year delay in SDA. What does that gap mean in real terms?
It means a massive 7-year gap in robust cislunar domain awareness, while over 100 missions are planned for the moon in that same time frame. We will be operating blind, while our competitors are setting up infrastructure.
So it's the stopgap.
The USSF is actively encouraging commercial and international partners to use optical and radio frequency sensors, and is pushing for common international standards for beacons on all spacecraft, just to help identify and track objects in that vast volume.
Okay. The second capability is communication, which becomes incredibly difficult over nearly 250,000 miles.
High bandwidth communication is a major technological hurdle. Traditional radio frequencies struggle to support the massive data transfers required by a sustained lunar industrial presence. laser communication is the ideal solution.
And that's been proven out, right?
It's been proven viable by the deep space optical communication payload aboard NASA's Psyche spacecraft, which successfully transmitted and received data across nearly 10 million miles. A necessary step is placing a series of relay satellites at key Lagrange points to assure uninterrupted high-capacity connectivity back to Earth.
And finally, PNT, we basically need to extend GPS into the cislunar environment.
Exactly. Position, navigation, and timing are the backbone of modern military and commercial operations. The USSF is uniquely positioned to lead the R&D to establish the standards for cislunar PNT, providing astronauts and robotic missions with a common, accurate reference for safe travel and maneuverability, which is critical for docking an LEO and landing on the moon.
To truly enable industrial scale and hard power capability in this deep space environment, the DoD also needs to accelerate R&D in new propulsion and power technologies that are far more efficient than our current chemical rockets.
That demands a leap into nuclear propulsion. DARPA, the Defense Advanced Research Projects Agency, is running a program called DARICO, the Demonstration Rocket for Agile Cislunar Operations. They are researching the viability of nuclear thermal rockets.
And what does nuclear thermal propulsion offer over chemical propulsion?
It provides a massive increase in propellant efficiency. That means you can achieve faster transit times and significantly more delta V, which is the measure of a spacecraft's ability to change velocity. This is necessary for the rapid, responsive maneuverability required for both military and commercial supply operations in deep space.
And power generation is critical, especially for enduring that 2-week lunar night.
We need both power generation and power beaming. AFRL is working on 2 key programs. The first is Jets Joint Emergent Technology supplying on-orbit nuclear power, which explores advanced spacecraft power generation.
And the second?
Complementary to that is SSPIDR, Space Solar Power Incremental Demonstrations and Research. This is exploring the concept of beaming power to remote users, like a rover or a habitat operating in the lunar night from an orbital satellite or a nearby lunar station. Power beaming is a necessity to sustain long-duration, high-power industrial operations.
Okay, finally, let's talk about the sheer logistics of industrial launch on the moon. If we're launching 100-ton starships, how do we handle that regolith problem?
This is a major engineering problem because there is no atmosphere. You can't use aerodynamic controls like wings or parachutes. Yeah. When a powerful rocket fires its engine near the surface, it just blasts that jagged regolith everywhere.
So to sustain industrial operations, you have to limit that dust dispersion.
Right. And the futuristic solutions range from building high-tech launch pads that direct thrust away from the surface to non-rocket launch systems.
Like a surface-based launch system.
Exactly. Ideas include a high-tech electromagnetic rail system, similar in principle to what is used to launch jets off modern aircraft carriers. Such a system could accelerate a payload to a predetermined altitude off the lunar surface so that when the rocket engines engage, they don't dislodge the harmful regolith. It's a necessary infrastructure investment to preserve the environment for sustainable, long-term industrialization.
This all sounds like an enormous multi-billion-dollar undertaking. Right. What is the analyst recommendation for securing this future?
The consensus recommendation is that modest, targeted early investment now prevents massive, costly intervention later. Specifically, analysts recommend Congress fund additive growth of about $250 million a year to the Space Force budget, combined with an increase of about 200 personnel dedicated to developing the necessary cadre of cislunar experts.
And the cost of not doing it?
The failure to make this investment now means ceding the initiative to China and Russia, allowing them to establish unfavorable norms and advantages that we would then have to spend exponentially more to overcome. The military's imperative is not to seek conflict, but to establish the safe, stable conditions, the critical infrastructure, that allow peaceful, cooperative civil and commercial industrialization to flourish first.
So we've traced the entire arc of this revolution. The Starship singularity provides the economic potential to end the politics of planetary scarcity, promising vast energy and material abundance. Effective accelerationism provides the ideological imperative, demanding that we move quickly to seize that potential, even at the cost of existing comfort and regulatory caution. And that opening frontier immediately triggers a geopolitical race for strategic resources like lunar ice, forcing us to choose between 2 competing visions for the future of the solar system.
The core shift is complete. Humanity is transitioning from passively gazing at the stars to actively utilizing the moon as a resource base and an economic springboard for the entire solar system. This requires immense, industrial scale construction, and it is immediately triggering a geopolitical conflict. The norms and infrastructure established in the cislunar regime today, whether they are cooperative, transparent, and resource sharing under the Artemis Accords, or territorial, coercive, and denying access under the China-Russia ILRS approach, will absolutely define the global balance of power for the rest of the 21st century.
It's the ultimate choice facing policymakers, engineers, and industry. Continue the trend of managed decline and regulatory stagnation on a single, fragile planet, or embrace the brutal, freezing frontier that demands construction, investment, and exponential growth. The ultimate measure of success in this new era will not be measured by the poetry of the human spirit or the eloquence of exploration speeches, but by the sheer tonnage of cargo hauled, the speed of technological adoption, and the ability to pour concrete first.